Okay, so I'm going to talk about bounded Kolmogorov complexity based on cognitive models and pattern discovery. So in nature, discovering spatial and temporal patterns can be essential for finding resources and avoiding dangers, for example. So here are some examples. Strawberries ripen in June, chanterelles grow on north slopes. Where there are seagulls, there is fish. That bear is aggressive. There will be a storm tonight. There are some patterns there that are could be worth observing. And why is this relevant to AGI? Well, because there's huge evolution pressure on the ability to discover patterns to begin with. And there is also a strong correlation between pattern discovery and general intelligence. So it's reasonable to require that AGI agents should be able to do pattern recognition, pattern discovery as well, on the human level and beyond. And as you know, IQ tests, there are lots of pattern discovery problems in IQ tests. For example, progressive matrix problems and number sequence problems. And we're going to look more closely at patterns in number sequences. So here is one number sequence, for example. What would the next number be there? Well, I think we would all agree that it should be 111. And here's a harder one. Take a look at it. What's going on here? Well, actually, it's going to be 256, because if you multiply the two previous numbers, you're going to get that number, right? So like a Fibonacci variation. Okay, so how did we do when we solved these problems? Well, we wanted to find a way to go from 105 to 107, for example, in the first example. And how could we do that? What would be the easiest way to go there? Well, I think by adding 2. And then the next, and then the other sequence, then we were to go from 2 and 2, the first two numbers, to 4. How can we do that? Well, we could either add them or we could multiply them. And then we look at the next pair in the sequence. Then we have to go from 4 and 8 to 32. And that we can only do by multiplying them. So then we conclude that, yeah, we multiply the two last terms. Okay, so yeah, what were we doing here? Maybe we were looking for short expressions that would explain the next number, describe the transitions. And if we're doing that, we're using some kind of some version of Ockhams razor. And there are many versions of many formal complexity measures that in some way capture versions of Ockhams razor. Kolmogorov complexity, for example, which has the drawback of being uncomputable, as you know. And also Solomonov probability or complexity, as we heard about yesterday, is also uncomputable. And a third one is the Levin complexity, which is computable, but it depends on two arbitrary choices, the universal Turing machine and adding the log of the runtime as a term. So if we look at machines now, the state of the art when it comes to solving number sequence problems, there are many software packages that have specialized modules or functions for solving those particular problems. For example, Mathematica, Maple, the online encyclopedia of integer sequences, and WolframAlpha. And we tried those tests on some IQ tests, on some number sequences of IQ tests, and got fairly poor results. It turns out that they perform below the average human level. So something else is needed, maybe. And if we look more carefully at what we're doing when we're solving these problems, we can discover that they are fairly subjective. For example, if we take this ridiculously simple question, 1, 2, then what comes next? Well, you can argue for many things there. Maybe it's going to be a repetition, 1, 2, 1, 2. Maybe you want it to be mirrored, 1, 2, 2, 1, or a successor, 1, 2, 3, 4, or you're doubling all the time, 1, 2, 4, 8, and so on. Which one is better? It's subjective, I guess. They look like purely mathematical questions because they involve numbers, but they're not. There's a psychological dimension there. So this subjectivity depends on many things, actually, on what we prefer, as we saw, and on what we know also. So this number sequence, I don't think, it's the busy beaver sequence. And the next number happens to be 107 there. And how could anyone figure out that who doesn't know it? Pretty impossible. And it also depends on what we can compute. So let's look at that sequence again, 2, 2, 4, 8, Fibonacci-like sequence. Yeah, we know what the next number is in principle, but we can't compute it, at least, if we're like normal people, not that quickly. So, yeah, this subjectivity is well known, and Wittgenstein, for example, argued that we can always argue for any continuation of any number sequence. For example, just by repeating it. That's one possibility. But in real life, we can't say that this problem doesn't really exist. It's purely subjective, because in real life, our predictions will be either right or wrong. And we get rewarded if we get them right and punished if we get them wrong. So there is a notion of right and wrong there. And the same holds for IQ tests. You will get a point if you answer a certain number, and if you don't, you won't. So we have to take the consequences of this subjectivity now. And we're going to do that by introducing a subject, actually, into our computational model. And a subject, in this case, will be a cognitive model. And we can use a very rough cognitive model. It's sufficient, of some imagined human problem solver, which can be a fairly strong human problem solver. And the only thing that we need is a notion of term that we're going to use to describe the sequences, and also a framework, a computational framework for evaluating those terms, computing them. So the terms are formed on the basis of this vocabulary: some digits, some operators, the ordinary arithmetical operators, and we have a juxtaposition operator for turning digits into numbers. And we also have a unary function symbol, which will be used for denoting previous elements in the sequence, and a variable n, which will be the position of the sequence, position in the sequence. And from this vocabulary, we define the terms as usual and as expected. So here are some examples how we can use this cognitive model. Sequences, yeah, for example, 103, 105 is generated by that one. The previous number in the sequence plus 2. This one that we saw is generated by the two previous ones, and the factorial here is generated by that term. So we can generate a lot of terms, a lot of sequences by these terms. And we have a framework for evaluating terms as well, with some standard table entries, some standard algebraic rules, and a maximum term size, which will model the working memory, primitive version of the working memory. The terms can only have size 8, say. And then we have an algorithm which we use for evaluating the terms using these rules, with the restriction that the width is never more than 8. Okay, and then we get a complexity measure out of this, because we take the length of the shortest term that generates the input sequence, but we use the following essential restriction. All positions of the input sequence plus the next position must be computable in the cognitive model. And when we do that, that's the only thing we do. And then we can we get our program, which is this one. First we look at Mathematica and the other ones. And here are 3 IQ tests. And yeah, the maximum is 11 on that one, 29 and 36. But performance, it's very bad performance. And when we use this simple method, we get pretty good performance. These two don't really count because we used them when we made the program. But this one we haven't seen before. So yeah. And the generality here, many pattern discovery problems can be encoded as number sequence problems, as you know. And we also used the language of arithmetic in this case, but the same strategy works for other terms and term rewrite systems as well. So we conclude here that in AGI we aim for human level performance and beyond. And to that end we can exploit both the strengths, as we often try to do, and also the limitations of human reasoning. And in this particular case we exploited the limitations in the human cognitive resources in order to reduce the size of the search space. And thereby we reduce the computational complexity. So we suggested a version of Kolmogorov complexity, a bounded version that is feasibly computable, directly derived from the goal of reaching human level performance, and applicable to arbitrary term rewriting systems. And we got some encouraging results on the IQ test problems, but more work is needed here, I think. Yeah, thank you.
Okay, we have plenty of time for questions.
So when Simon and Kotovsky worked on number sequences back in the early 60s, early to mid 60s, they argued for their model in that not only did it do well, human level performance, but when it made a mistake, it tended to get the same wrong answer that people got, and they could explain that it got it for the same reason. So how does your system?
I think that could happen.
Mistakes?
That could happen here too, with this one too. The same thing.
It can or it does?
Well, I mean, it depends on which person makes what mistake. But in general, it can, because we are looking for simple arithmetical expressions, just like most people, I suppose. And we have limited cognitive resources in the model, just like most people. So we can come up with different answers sometimes. It doesn't always produce a unique answer. And then we have other tie-breaking mechanisms to do it. But we haven't made a particular study of what happens when our program answers incorrectly and compare them to incorrect answers of people. That could be interesting to do. Exactly.
What's the method by which it tests hypotheses?
It's just like brute force, you can say. And it's easy because we can, once we have a term which is a candidate description of a sequence, then we can abort the search as soon as the term doesn't compute the term correctly, or as soon as the term takes too long to compute it. Because we are using the bounded resources, and that means that all our computations will be fast. Because if they're not fast, we're just going to abort them.
So you have some heuristics on the time, on measuring the time?
No, we don't need to have that. We don't need any heuristic really, because we just we just do brute force in this small and finite search space.
But the upper limit then is then decided by, in fact, the exhaustion of the methods, or I mean.
Yes, exactly. It can happen that we fail, and then we go through all possible terms and check them, and if we don't find anyone that matches with the available resources, then we return fail. We don't always provide answers, just like humans.
Other questions? Yeah.
Yeah, so you mentioned the first two IQ tests do not actually count.
No.
So I'm wondering, how did you use them in your framework?
Well, we failed on some tests, and then we introduced, we used them to fine-tune the tie-breaking mechanisms, for example. And I also think that we introduced division as a result of looking at those tests beforehand.
Other questions? Okay, let's move on
Okay,
to the next paper.
to the next paper. Yeah. Yeah. Right.